So now we know that the B12 is equal to B21. Then we reformulate the three equation again, since we have one more information given. So at the beginning we have a B12, B21, A21. Now we try to make it simpler. Since B12 is B21, we only leave the F1 times 1 F2. The different part outside and put the same coefficient at the top. So R12 is a rate of some R times F1 times 1 minus F2. This is the rate of absorption. And this is the rate of the stimulated emission. The coefficient is the same. Then the third one, although they are correlated, but we just currently we just pull out another rate with a different one, since we still call it different. Although these two values still is built, it's linked between by the density of mole of the Okay, it's written like this one. And now we have another implication here. First, if you're seeing this number, if this is a real number, under no excitation, the lowest number, the R12 will be a very high F1 and a very low F2. That means all the electrons flowing to at its lowest state. So how high could F1 be? It's at the most 1. It cannot be 1.2 or 1.3. So the highest number of 1, F1 is 1. Similarly, if it's under 0K, because there's no any electron at the higher state, the smaller value of F2 is 0. So the absorption rate is limited. It has some maximum number called RR. In reverse, if you excite your material very strongly, how large the gain it could be is also the case. At the most, F2 equal to 1 and F1 equal to 0. That means you really compare it hard. All the electrons in the level 1 is excited to the electron level 2. Then the stimulated emission rate at the most will be equal to the R12. So it's a bounded value. So the transition rate even under extreme excitation, it doesn't go. It has an upper limit and a lower limit. That will depend on your density of state. We will see that when we further expand that. Similar, same as the RSP, it also has a limited value. It's also bounded by your density of mole in your cavity. So, since we already said that the R1, we already found that R12 and R21 is a pair reaction. And let's put the spontaneous emission aside. First, we define something called the net stimulated emission. Since we already counted the absorption as a part of the stimulated emission, RST. As that RST defined is R21 divided by R12. Okay, naturally that will be F1 minus F1 F2 divided by F2 divided times F4 to F1. So the final result will be RR times F2 subtract F1. So what if the material is transparent? Well, we consider something is transparent. For example, this glass is transparent. That means the light will enter without increasing or decreasing. How many light comes in? How many light comes out? If the light intensity decrease, you will see the part will be darker. If it increase, you will see it's emitting light. So it's not transparent. So the more transparent, we have a more specific definition. It's called that light passing that remains the same intensity after passing this solid. For most of the case, we are considering the transparent world. It's because the RR is 0 for the case. For example, for this glass, when light comes in, although the electron is all in the lower density of state, but because there's no state here, so the RR dot equal to 0. So that's when you consider the glass is transparent. However, even the light coming in is not, you have a certain density of the R here, but it is still possible to let a specific light coming in and leaving in with the same density. That only happens when F2 is equal to F1. So that's another transparent condition for semiconductor when F2 equal to F1. Then we further write it out F2 and F1 as F2 equal to F1. That means the electron at the level 2 is probability at the minus is quasi-Fermi level divided by kT minus plus 1 is equal to the exponential E1 minus EFB kT plus 1%. So we just take an inverse. So basically these two exponential have to be the same. So E2 minus EFC should be E1 minus EFB. So E2 minus E1 is the frequency of such light should be equal to the separation of Fermi level. So when does the light become transparent to the semiconductor? That happens only when this piece of material is under excitation. So the Fermi level of electron holes start to separate. And while it is strong enough, the EMC and the EFB separates and equal to the energy of incoming light. Then the absorption and the stimulated emission share the same transition rate. Then this light becomes transparent. Okay. But what about the light with the energy less or higher than the Fermi level separation? Let's consider this is the case that the semiconductor is excited to Fc to some level and the Fv to some level, for example, like this. Then if the transition of the band from any vertical transition for that one with the transition equal to the separation of Fermi level, it's transparent. If your transition is a little bit further, for example, for this one to this one, then for this case, if the transition is from E2 with even higher E2 and even lower E1, it's the state vacant here and the more electrons at the lower level. So theoretically, the upward transition is still more likely. So for the light with HμT1 larger than delta EF, delta EF means the separation of the quasi-Fermi levels, it's still absorbing. That means the light will be decaying, passing through such semiconductor. But in the other way, if the Fermi level separation is this large, what happens if the light coming in is at its band edge? For the light incoming energy, you encounter the more higher probability of the electrons at higher state. So the stimulated emission will dominate over the absorption. So the light in the other side will be propagating. Then we call it gain. So if the F2 is larger than F1, then EFC then minus EF3 is larger than if F2 is larger than F1, then your total stimulated emission is positive. So you have some gain. So what does a word called the population inversion in the laser you commonly know? At the beginning, in the two-level system, that will tell you that N2 should be larger than N1. That's the concept of this word comes in. Since it's a two-level system, the number of the lower state and the number of higher state is equal. So in under population inversion, N2 should be higher than N1. It's more intuitive explanation. But in semiconductors or some more complex systems with impurities in the middle level, the real definition of population inversion is the F2 larger than F1. That means under such excitation, the probability of occupancy at high level is higher than the low level. That is enough. So you don't need to compute really hard. If the high level have only 26, but your low level has 100, then you excite 10 electrons from lower level to higher level. So that will be easier just to draw a figure. If the lower level or the high, let's start with higher level. Higher level has 56, and the lower level also has 56 or 56 anyway. Then you want to pump more electron from low to high. That means you have to you have more than 25 and less than 25 and occupation here. Assuming the total is 56, then you reach a population inversion. However, let's consider another case. If the higher state has only 10 seats, and the lower state has 100, and the total, let's call people. Yeah, let's make it more big. It's originally 100 people at the lowest side, since all the low state is occupied. If you only excite 10 people upward, then it becomes 90 people. Then it has 10. Oh, okay, fully filled. So at such case, what is your occupancy rate? So it's 10 over 10. So F2 is equal to 1. But in this way, what's the occupancy level over here now? It's 90 over 100. So the F1 is 0.9. Then F2 is larger than F1. It will still undergo optical gain. You don't really need to pump half of your the carriers from low level to high. So this material could remain stable under a strong non-equilibrium state or under a population inversion. So this is another conceptual drawing. Consider this is the bottom axis is energy, and the band gap is here. So if a material is excited by light, and your P, probably okay, it is injected by electron, then your EO spectrum probably is around here. Then if you injected the electron much harder, you have a lot of electron at top and a lot of at the bottom. The difference or the Fermi level is increasing. While it is increasing over Eg, then the light below delta EF will experience gap. But it also needs to be above Eg. Because when the light is less than Eg, there will be no state for both. So the transition rate will be 0. Since we're talking about gap, the transition rate should be a real number larger than 0. So they give you a positive gap bandwidth from Eg to delta EF. If your incoming light has an energy higher than your delta EF, it's still absorbing. So if you wanted the material to provide gap with higher energy, you need to shift the Fermi level also to the higher side. That means you need to pump harder to generate more electrons at the valence band and more holes in the conduction band. So the Fermi level will keep increasing for EFC and then decreasing for the EFB. Okay, so let's take a rest.